Okay, so it's on record. All right, okay. So what we talked about production of entropy, and then okay, let's go to the third law. All right, control third law. Okay. Now, yeah. So you know that there are four laws in thermodynamics: the zeroth, the first, second, and the third law. And the third law is kind of a hypothesis, not quite a proved one, or no, there's no uh, uh, substantial evidence for the measurement of it. Talks about measurement of entropy at absolute zero, and you know that absolute zero temperature is still not reached. Exactly absolute zero has not been reached yet, and at those low temperatures, what would be the entropy? And that's what the law is all about. So it says it starts with the non-seat theorem. The entropy change accompanying of any physical or chemical transformation approaches zero as the temperature approaches zero. So the whole idea, if you look at the Maxwell curve, or the um, Maxwell-Boltzmann distribution curve, you'd see that as you go down in temperature, the specific heat of the substance sort of goes down. And that is because you heat, or enthalpy, or internal energy, so to speak, uh, is a derivation of um, the thermal motions, vibrations that you have in a material, and that scales down with temperature. As the temperature goes down, the vibrations, of course, goes down. They go down, and at absolute zero, it is expected that there is no vibration at all. So to speak, when there is no vibration, there is no specific heat, right? And you know that entropy is scales with the specific heat, in the sense that it scales with Cp by T, right? So that part again becomes zero. So the entropy change over any process, when you go to lower and lower temperature, it keeps on decreasing. And it's said that at absolute zero, it's completely zero, right? Now, there are a couple of things that come out as a corollary in these arguments, is that in absolute zero, so uh, then you cannot have something like a gaseous substance or a liquid substance. Everything has to be in a solid substance, because if some substance can exist in a liquid form, then its solid form, its a solid state, would also would have an entropy lower than the liquid state. Okay, so how can a liquid state exist in absolute zero, where there is another state which has a lower entropy? Okay, so on that count, you would say that at absolute zero, everything is solid. Now the question then becomes that if you have a solid, are there many forms of the same solid which have different entropy? All right, so that's a question you must ask yourself. Let's say, for example, if I have a sodium chloride, uh, or for that matter, any material, uh, does that material have another form which has a slightly higher entropy or slightly lower entropy? Yes, that's possible. That's possible because in a solid substance, you might have different kinds of crystal structures. You have different crystal structures in the glass, for example, in cubic, tetragonal, orthorhombic, or hexagonal, or triclinic, and these kind of things. So and those are symmetry operated, in the sense that a cubic structure has a certain amount of symmetry that the tetragonal doesn't have, or an orthorhombic material would have a different kind of symmetry. And it is said that cubic would have the highest amount of symmetry, and the triclinic kind of materials would have the lowest amount of symmetry. So when you say that they have the lowest amount of symmetry, then you would think that they have a slightly higher amount of entropy. Because more symmetry is more ordered. More ordered means less entropy, right? When you say a little less ordered, that means it is a slightly higher entropy. Okay? That we can do some calculations in a particular material, and then what kind of um, entropy changes happens um, when you transform from one kind of a phase to another kind of phase, from an alpha phase to a beta phase, the beta phase to a gamma phase. There's some sort of entropy change involved, albeit the entropy, the delta change is fairly low, but then there is a change nevertheless, right? So so when we say that in absolute zero, then you will have a solid, and you cannot have different kinds of solids. Okay, that's on the crystallographic part, or different kind of crystals of the same solid. On that approach, can we have different entropies? That's the question. But another question is, let's say even if you have the same kind of crystal, okay, but the crystal has mm, defects in it. Are you guys aware of things called point defects in a material or line defects in materials? I know some of these things will be treated in your subsequent semester when Pratyasa speaks about structure and properties of ceramics or materials in general. Uh, the point defects, I think you might have read in 10 plus 2 or something, at least brief of it. Okay. Now, the thing is that, in a regular crystal lattice, if those lattice points are missing, okay, or the lattice points of substance A is filled with something like a B, then those are called defects, and those are called point defects, referring to individual lattice points, individual either absence of a material or presence of another material in those lattice points in a host crystal. They constitute sort of defects, and the very fact that there are defects, that means there is some amount of entropy, because in a matrix of alpha atoms, if you have a beta kind of material, then it sort of increases the entropy. So that would mean you would, at absolute zero, would not have a material which has defects. All right. So at absolute zero, everything is supposed to be completely ordered. All right. But despite that, if you even if you have some kind of a regular arrangement of a material, it's only regular to an extent. It's not completely regular that it would not have entropy at all. If you go to the basic definition of entropy, what is it? It's how many different ways you can have the energy diagrams, energy bands, or energy uh, points distributed among the constituents. If it is just one way of distributing it, then the entropy is the lowest. If there are more than one ways, if you natural logarithm of more than one is, it's always going to be something. It cannot be zero. So it's I don't know. It's sort of a hypothesis yet, so to speak, not a complete law as such, because there is absolutely no proof, but then analytical arguments only. That said, so it is because uh, um, that it's because that at absolute zero there will be no perfectly ordered crystal, because at absolute zero entropy is zero, or at absolute zero there can only be perfectly ordered crystals. That's why the entropy is going to be zero. I am not too sure as to what leads to the other. Okay, that's a bigger question. But then, yeah, for a practical point of view, let's say that when you go to absolute zero, the entropy is completely zero. And let's leave an option open, saying that there could be some amount of residual entropy. All right, but then there will be no change of entropy at that stage. Okay. So that's the practical aspect, is that when you go completely towards zero. There is no entropy at all. And something that we can use in our practice or in our understanding is that when the temperature is much lower, the entropy contribution has to come down. It's going to be really low. Okay. So the final line is that the entropy of all perfectly crystalline substances is zero at absolute zero. So that's it. That's about the third law of thermodynamics. Okay, in that line, we should sort of um, try and discuss something about equilibrium, as to what leads to equilibrium and what leads to, or what is it that sort of makes a process uh, continue or go, or a process happens. uh, because these two are completely opposite, because when there is a process happening, then it's slightly away from equilibrium. When the system is at equilibrium, then there is no process happening, right? And this is something you can think of a material system, or melting of material, or the expansion or contraction of a piston, uh, and a cylinder, anything of that sort. Okay. So let's discuss something about that. So when you combine the first and the second law, then you can write the change in internal energy is TdS minus PdV, right? That, it's sort of easy to understand, because TdS. So the first law is what? Du is dq minus pdv. Dq is the heat, and the second law says that dq is TdS, or ds. This ds is dq reversible by the temperature. Okay, so instead of in place of dq, if you write TdS, then this becomes du is TdS minus pdv. This is a more useful form of the first and second law. From this, you can derive the criteria for equilibrium, which we can write as, it's, you got to think about it slightly. In a system of constant internal energy and constant volume, the entropy has its maximum value. Right? When talking about system, I mean, you can think about some gases in a chamber, and in that situation, when we are not changing the internal energy is constant. That means del U is zero, and let's say we are not changing the volume itself. It's a material or a system of constant volume, well-bound volume, for example, a gas in a container, a fixed container. Now, in that sense, equilibrium is maintained when the entropy has its maximum value. That means if that is the situation, if you're not changing the internal energy of a system, and if the constant, the volume is fixed constant, then entropy would have its maximum value. The system would maximize its entropy, and that's where equilibrium will be maintained. Or when, as long as the entropy is at the max level, then there will be equilibrium. All right. And the second part is that there's another way you can say or define equilibrium, is that in a system of constant entropy and constant volume, the internal energy has its minimum value. Well, like talk about the same constant volume system. So all in all, we are talking about here a constant volume system, right? And the constant volume system, if you if you if you don't change the entropy, right, then the internal energy would be minimum, and that would define equilibrium, right? So this is a combination of processes, and these processes, or some maximum or some minimum, actually comes with some kind of a preconditioning. Now here, it's of course both the systems are constant volume systems. Here you say that there'll be internal energy is constant, and that's where the entropy would be maximum. And here the entropy is constant. That's where the internal energy is maximum. Right. you can look at it from a mathematical point of view, is that when the Clausius inequality says that dq reversible is either equal to or greater than dq. All right,
Sir,
that's yeah.
sir, that last slide say that internal energy has given minimum value, sir. You have
Internal energy, yeah, that's right. Internal energy has to be minimum value. Yeah,
yes, sir.
that's what the point is. See, one part of energy has to minimize, and the other part of not quite energy, but then energy conjugate has to maximize. So that is something you can define equilibrium in either of the ways. All right, which seems slightly complicated. And we'll try to see how we can simplify it. All right, so hold on a moment.
Yes, sir. Got
Yeah. So I don't know if I've told you explicitly the Clausius inequality, but then it's simple that when we talked about heat change in a reversible process and an irreversible process, right? So the heat change in a reversible process is always higher. Okay, and that would lead to the changes in entropy in a reversible process vis-a-vis irreversible process. But simply you can get this thing is that the heat change in a reversible process is higher than the heat change in a irreversible process. At least it will be equal, right? Okay. Now that so dqr we convert that thing to TdS. All right, and let's say if in the dq part we take of the constant volume process, then from the first law you can write dq is du plus pdv, and if you do that dq in a constant volume process, then it's simply equal to du. All right, so that would mean that TdS uh, is greater than or equal to dqv, and which is again du. That means TdS is greater than or equal to du. Right? That would mean that if you look at the change in entropy, the ds, that's an infinitesimal change in entropy in a system of constant internal energy and constant volume. Of course, we are talking about here all the cases a constant volume case, so this remains fixed as a constant volume system. Then this ds, when internal energy is fixed, is going to be greater than or equal to 0. Likewise, if you talk about du, this du at constant volume, of course, is there, and at constant entropy is going to be less than 0, less than or equal to 0. So these are the two conditions that entropy has to maximize and internal energy has to minimize in a constant volume process. And this entropy thing, the maximization of entropy is applicable to a constant internal energy system, and the minimization of internal energy has to work for a constant volume system. And when you do the entropy, you make the entropy constant. So the point that is coming out from here is that we are left to control things like an entropy or an internal energy, or you have make the system a constant volume system. So these are some of the inconvenient processes that probably a solid state uh, chemist or a solid state physicist would encounter, or a material scientist would encounter, right? So is there other ways uh, to sort of simplify the conditions of equilibrium? Okay. Now, these here we only talked about the constant volume system and systems with reference to internal energy only, which perhaps is okay, sort of works well for mechanical engineers. So we need to figure out our way of finding out equilibrium in material systems. So we need to look farther in that sense. All right. So as I said, when you talk about a change or spontaneous change or things that happen, processes that happen, um, for them, it's V and S are inconvenient variables to control. It's not easy to control them. Um, Yet again, when we talk about the observations in the domain of chemical and materials thermodynamics, we generally deal with constant pressure, right? So with those things in mind, and with those things being slightly different than what we talked about in the constant volume process, how can we look at how can we have an idea about spontaneity of a reaction, and would that reaction happen or would it not happen? Can we have an idea about that? When I say spontaneous reaction or spontaneous change or something in the domain of thermodynamics, we are not concerned as to how fast or how slow those things would happen. All right, that's a completely different aspect which is treated in kinetics. All right, here we are talking about whether that will happen or not. Okay, that's why now if we invoke the sort of literature, you know, to be or not to be, have you heard of this term, this phrase, to be or not to be? That is the question. Anyone? कोई वो हैदर वैदर मूवी कोई नहीं दिखता है क्या? वो पुराना तो छोड़िए. So that's a Shakespearean sort of क्या उसको बोलते हैं, dialogue or phrase you would say, to be or not to be. So to be or not to be, that is thermodynamics. That's not literature. In the domain of thermodynamics, I always say that to be or not to be, that is thermodynamics, because thermodynamics tells you whether something will happen or not. It doesn't tell you, whether how fast things could happen or how slow things would happen. That's a completely different thing altogether. Okay, whether it will happen or not, given the conditions. So that is thermodynamics, right? And we are able to say that that's based on one aspect, which is what we're going to be talking about right now. Okay. Now, in the context of spontaneous change, let us ask a few questions to ourselves. Okay. Now, are endothermic reactions spontaneous? Right? Are you guys aware of exothermic and endothermic reactions? I think you must be aware of, right? Okay. Now, if the question is, yeah, of course, are endothermic reactions spontaneous? Is an exothermic reaction spontaneous? Right? Are all exothermic reactions spontaneous? Okay. And if there is no direct answer to that, then what governs spontaneity? Right? And you know that spontaneity and stability are just reverse of each other, isn't it? Because something happening spontaneously, that means that it's not stable. Right? And something which is stable, that means the system is in equilibrium. That means the spontaneity is not the case. Right? Only a change in stability would kind of lead to spontaneous reactions. And if endothermic reaction is spontaneous, or if all endothermic reactions are spontaneous, then exothermic reactions will be non-spontaneous. Is that the case? No, that's not the case. Again, there are so many examples you can find out. You can perhaps should think about it yourself. Um, the basic observations that you might have had in your daily lives and lives, or things that you do in the laboratory. From those things, you can derive those observations. I just put in one or two examples. So dissolution of ammonium nitrate in water, of course, that's an endothermic reaction. Okay, that also tells us that is dissolution an endothermic reaction? Anyone? All dissolution reactions, are they endothermic? No, they are not. If you're thinking that all, like, you put some salt into water, it sort of dissolves, that's dissolution. Then there is, the heat involved with that is heat of dissolution. um, that is not always endothermic or exothermic. It can be different depending on the kind of material that you're trying to dissolve. All right, and sometimes you sort of put some salts into water, make an aqueous solution of that, and if you hold the beaker, then you'll see that it's slightly cold, than what it was before the solution. That sort of tells you that it's an endothermic reaction happening. But at the same time, if you put something else, like for example, the dissolution of sodium hydroxide or potassium hydroxide in water, and you shake it up well and then make sure that it's completely dissolved, and you hold the beaker, then you would see that the beaker is kind of warm. That means that's an exothermic reaction happening there, and that also is part of the dissolution process. So you cannot directly say that whether it is endothermic or exothermic reaction as such. But then, if you look at it, both the reactions are happening spontaneously. All right, you don't have to do anything else. Naturally, in the given circumstances, given that you have 1 atmosphere pressure and normal temperature like 298 K, then you'd see that those ammonium nitrate dissolves as well as potassium hydroxide dissolves in water. On the one hand, one makes the solution cold, that means it's an endothermic reaction. The other, the sodium hydroxide or potassium hydroxide, they make the solution warm, that means it's an exothermic reaction. Likewise, burning of carbon, you know that this oxidation of carbon, that's an exothermic reaction, but it happens spontaneously. It can happen in normal atmosphere pressure and all. So, is there a relationship between spontaneity um, and whether the reaction is exothermic or endothermic? Perhaps not. All right. Are all exothermic reactions spontaneous in that sense? If the solution of potassium hydroxide, let's say, if it's slightly different in only in the solution part, but let's say if all exothermic reactions are the reactions which lead to evolution of energy, evolution of heat. Okay. Would that mean all reactions spontaneous? Like, for example, the formation of nitrogen oxide or the freezing of water at 1 atmosphere. If freezing of water is spontaneous, then melting of water is not spontaneous. All right. So it's complicated. That means when we're talking about finding a relationship between spontaneity or stability with whether the reaction is exothermic or endothermic. Okay, if you're trying to address those questions, then what is it that we're trying to find out? What is it that is a point of interest in an exothermic reaction or an endothermic reaction? What defines that? Anyone?
Kind of heat associated in the process. So heat, like
Heat.
so some
Heat
yes, sir.
meaning DQ or what?
So Q obviously. So Q like heat change, like so
Q
and
changes.
those yes, sir.
Okay, anyone else? When we're talking about
Energy
energy, what kind of energy?
and the energy barrier.
No, energy, no, we are not talking about energy barrier here. Are you talking about, do you define exothermic reaction or endothermic reaction based on the energy barrier?
No,
How
sir.
do you define the exothermic reaction or endothermic reaction? What is it? Is it internal energy or it's entropy or it's enthalpy or it's work
It's
or
enthalpy.
that's right.
Yes, sir.
It's
It is.
enthalpy, isn't it? Is it when we
Yes, sir.
define an endothermic or exothermic reaction, is you talk about del U or del S or del H or what?
So del H.
Del
Del
H,
H.
all right?
Yes,
So we are
sir.
talking about enthalpy here, isn't it? So when you're talking about enthalpy, and we're trying to define whether the reaction is spontaneous or not, and we are not finding an answer because an endothermic reaction can be spontaneous, an exothermic reaction is spontaneous, and there is no ground rule would say that all endothermic reactions are spontaneous or all exothermic reactions are spontaneous. That means there is something missing. All right, some exothermic reactions are spontaneous, some endothermic reactions are spontaneous, but will all of them are not. Okay, so there has to be some other parameter, okay, which will define spontaneity. Okay, enthalpy comes close because why do we worry about enthalpy? Because we cannot worry about internal energy all the time. Internal energy is sort of is a function of a constant volume kind of systems. Whereas we material scientists, we always deal with constant pressure systems. Okay, in that aspect, we'll have to refer things to enthalpy, not internal energy, right? But then we see that enthalpy is not actually leading to a final answer. Right? There's to be something else. What is that something? The something is that's free energy. All right. And this free energy is something which actually defines the stability of a system. Okay. We in the constant volume system, when we talked about, in a system of constant volume and no change in internal energy, then the entropy has to maximize. And in a constant volume system, when the entropy is kept constant, the internal energy has to minimize. Okay, those are the rules for that. So how can we make it a simplified rule? Is that by coining something called the concept of free energy. Free energy, the name comes, it's sort of easy to understand that this is the energy which is free, and this has to minimize. Okay, more free energy meaning more activity in the system. Look, it will not be in a stable form. More free energy in the system. So the system would always try to reduce that free energy and going through a process and leading to a situation where there is less free energy to deal with. All right. So in a constant volume system is what we talk about in the Helmholtz free energy. This is less the pressure volume work, whereas Gibbs free energy is something that we deal with that is in a combination of all sorts of heats and all sorts of work. Okay, and here it is A is defined as sometimes some books defined as an F as well. Now that's the first formulation of free energy. But then let's call it A. A is U minus Ts. And for a constant volume system, of course, you'd say that dA at constant temperature and constant volume is less than or equal to 0. Right? You can do it from here. Take about constant temperature, you get TdS here. And then for a constant temperature and constant volume system, dA has to minimize. So here we are not talking about what will happen to internal energy and what will happen to the entropy, like we defined here, right? So these things can be brought to a single point, that is this. dA has to go down. All right. Likewise, in a constant pressure kind of system, for material systems, we define something, the free energy is defined as Gibbs free energy. And this is after the name of J.W. Gibbs, this American thermodynamics person is probably the best known thermodynamics guy in the world with reference to materials and chemical thermodynamics. Incidentally, he's an American. All the development of thermodynamics thus far we've been talking about has kind of European origin. Starting from the development of heat and energy theory, heat and work theory, starting from the UK and going into the mainland Europe, when the concepts of entropy got developed and other things as well. But then the latest development of regards to chemical processes actually came from the US by Joshua Willard Gibbs. In his name, the constant pressure process based um, free energy has been named as Gibbs free energy, and that is the enthalpy minus Ts. Okay, and when you take a constant temperature process, is dH minus TdS, and this is what defines then equilibrium or the process, is that dG at constant temperature and constant pressure has to be less than zero. Right? That's where things will be spontaneous. Right? Now, to describe why it happens, or you know, is that if you look at this A part, right? When we are talking about du separately, that du has to minimize and ds has to maximize. Is that what we talked here, right? From this, okay. So if you look at this, it actually falls in line. If du has to minimize, it's got a lower number, all right. And if ds has got to maximize, then in the whole in the algebraic sum for dA, you'd see that let's say du, let's say nothing happens to du, all right. Now we say that ds goes up. What happens when ds goes up? So this becomes negative of a higher number, right? That means minus a bigger number. That means dA has to come down. All right, so dA sort of minimizes. Or let's say that nothing happens to ds. ds stays fixed what it is. Now du is coming down. So minimization of du also leads to a lower number. Right? So in isolation, minimization of du or maximization of ds, both of these things, either of these things or both of these things would lead to a lower number of dA, and that would lead to equilibrium. All right. Likewise, if you look at here, the enthalpy contribution and there's an entropy contribution. I would tell it is that these are both of these numbers are these expressions are energy expressions. All right, and dg is a combination of those energies, and in that energy, dH is one part, the enthalpy contribution, and TDS is the another energy part, which is the entropy contribution, which is the energy contribution from entropy change. Now, in a process which leads to a higher change in entropy or a positive change in entropy, okay, that would eventually increase this number, and minus of this big number would give you a lower value of dG. That would give to stabilization of the system, or the process would happen, a spontaneous process would happen. And the spontaneous processes happen because they want to get into equilibrium position. All right, spontaneous position happen because after the process they would get into an equilibrium position. So if the process involves a change in internal change in entropy in the positive, that means it is the entropy is going to increase in the process, then this would be positive. This is positive. Minus of this is a negative thing. So eventually the dg is a negative thing. Or dH by itself, if it is negative, then of course d is always negative. So when we talk about a system which is exothermic in nature, then this dH part is already negative. All right. So there is a good chance, there is no ground rule as such, but there is a good chance that this part, the process which is exothermic in nature, is more likely to be spontaneous, unless of course this is eclipsed by the TDS part. That means if this process is exothermic, that means this is negative already. So for this process to be not spontaneous, this ds part has to be so negative that minus TDS will be positive, and this will be more positive than the negative part of del H. In that process, dg would be positive, and therefore that exothermic reaction would not be a spontaneous one. Do you get what I'm saying? Typically, the exothermic reaction is more likely to be uh, a spontaneous process because DH by definition is negative. So you would expect DG to be negative, all right? But then for DG not to be negative, despite the fact that you have an exothermic reaction here, this part minus TDS has to be so positive, then this is more positive than this is negative. All right. And how this can happen? This can happen because not because of temperature, because temperature is always positive. So temperature alone cannot make this negative quantity a positive quantity. So temperature is going to be positive. So ds has to be negative, and ds being negative can make this total quantity a positive one. And ds has to be so negative that the ds, which is a negative one, multiplied by t, which is a positive one, this total becomes a big negative number, multiplied by this negative is a positive number, and that big positive number plus an exothermic reaction has to be so much that it sort of is totally is positive. Then and only then an exothermic reaction would not be spontaneous. Else, if there's a only subtle change in the ds and it's an exothermic reaction, this dg or this exothermic reaction is always going to be spontaneous. Likewise, you can have the discussions for an endothermic reaction. In an endothermic reaction, this dH is already positive. All right. So there's a good chance that all typically endothermic reactions might not be spontaneous. Right. But then for the endothermic reaction to be spontaneous, because this is positive, the total have to be negative, and the total have to be negative. This positive minus this much has to be, this TDS has to be largely positive. All right. If it is a larger positive, then this small positive minus this larger positive would be negative, and thus the endothermic reaction would be a spontaneous process. And how can this be large positive? If this ds goes for a higher positive number, if ds is positive, then an endothermic reaction has a chance to be a spontaneous process. So if you look at these things, there's a contribution of this DH, whether it's exothermic or endothermic, depending on its sign. And the driving force also is given by the what is the change that is happening in the process with regards to the change in entropy. Okay, so entropy change also has a role to play. Right, so in combination of these energy contributions, the negative, if it is negative, dg is negative, then it's going to be a spontaneous process. dg is positive, it's not going to be a spontaneous process. And when dg sort of equals to 0, that's where we would say that it's in equilibrium. Right? So that's it. That's what it is. We'll continue our discussions in the next class. We're getting into the core of thermodynamics. Okay, I hope it's sort of important. So we'll stop the recording here and we'll sort of take questions if you have. All right.